Well, it's been quite a year.
And as it comes to a close, we thank everyone who has supported Big Picture Science financially. We truly could not do the show without you.
One great thing that happened this year was the launch of the Big Picture Science page on Patreon. If you haven't donated yet, I encourage you to go to patreon.com/bigpicturescience and check it out.
It's a great way to throw your monthly spare change our way and get perks back in the form of exclusive rewards.
Anyone who joins us on Patreon gets access to early and ad-free versions of each episode. But if you give as little as $5 a month, you get access to exclusive bonus material.
For instance, you may be wondering what we have to say about the bizarre monoliths that have been mysteriously appearing and disappearing around the globe.
Or our take on recent news that a so-called Galactic Federation has been present on our planet for many years and in contact with seemingly random national officials.
These are the stories that you will find in our next installment of
Patreon exclusive bonus material.
So head over to patreon.com/bigpicturescience and join us. And thank you.
Thank you. We have rocks on the brain. NASA's launching new asteroid missions to study some ancient rock and ice balls and fill in pieces of a cosmic puzzle.
Scientists around the world are excited about looking at this sample and seeing what it shows us about how the solar system came to be.
It's one of many stories from this fall's American Geophysical Union meeting, that is, the AGU. Now, we can't attend the conference in the flesh, but we can report on some of its highlights, such as, well, how do you give an asteroid enough of a smack to change its path? I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute. In this episode, from asteroids to the Juno mission to Jupiter, to unusual effects of climate change in peat bogs and in the atmosphere over the massive Australian wildfires.
Everybody's seen the pictures of the mushroom cloud from the atom bomb over Hiroshima. A pyro-CB is like that. You get enough of a very rapid bubble of hot air from the fire that it actually will generate that thermal heat bubble.
The pandemic has limited our ability to meet in person, but even so, scientists continue their research, whether it's about the Earth or other solar system bodies. We'll bring you stories of heat plumes and rocks from space, or what we're calling this episode, fire clouds and ice-teroids.
Every year, tens of thousands of scientists gather for the American Geophysical Union Conference. Picture this: throngs of researchers mingling in a convention center, flogging their latest discoveries. Well, what seems so strange to me now is the idea of all those people physically in one space. Well, those days will return for sure.
Meanwhile, though, we checked in on the online AGU meeting, and one of the highlights was an update of NASA's Juno mission to Jupiter. The spacecraft is currently orbiting the giant planet, not around its waist, but in a polar orbit.
And Jupiter's a planet of extremes. To begin with, it's, the 800-pound gorilla, the largest planet in the solar system, with more mass than all the other planets combined. And it sports lethal radiation belts and the strongest magnetic field of all.
That's right. And scientists have a lot of questions about that magnetic field and how it interacts with the churning gases of Jupiter's atmosphere, as well as understanding the planet's well-known storms like the Big Red Spot. A member of NASA's Juno team gave me an overview of the mission at last year's AGU meeting, when people still spoke to each other the old-fashioned way. Well, one of the most intriguing things you said today, you said at the very end, which was the catchphrase for those working on the Juno mission is, "It's a whole new Jupiter." How so?
So what I would say is we sent Juno to Jupiter to do a bunch of measurements, and of course many of them were things that had never been measured before, or we were looking at the planet in a different way. And virtually everything we did in which we looked at Jupiter a different way, we got a surprise. So We looked at the North and South Poles for the first time, and we see they look totally different from the rest of the planet. We measured the magnetic field up close and personal and mapped it for the first time and found that its structure is much more complex and very different from what we expected. We used gravity to look for a dense core in the center, and what we found is something more complicated than that, where maybe there might be a core, but it looks like it's maybe spread out through, could be as much as half the planet. We used microwave radiometer to look at the deep atmosphere, to look beneath the clouds, and found that their structure is far down as we can see, hundreds of kilometers into the planet, down to where the pressure is hundreds of times the pressure here on the Earth. Before we got there, everybody thought you get below where the water cloud forms and you're below all the weather and everything should be smooth and simple, and it's not. And we still don't understand what's going on with Jupiter's atmosphere to make all that structure. We're working on it. We have fun new mysteries to solve, but we don't have the answers yet. So essentially, everything we did has shown us Jupiter is more complicated, more complex than we expected. And fairly early on, it was actually Mike Jansen with the microwave radiometer experiment said, just get used to it, guys. It's a whole new Jupiter. And I love that phrase, and so does everybody else.
Some of the images that were shown today showed what looked like cyclones, a certain number of, maybe a dozen cyclones or so on the surface of Jupiter. Well, it's actually not on the surface, is it? It's in the clouds. The clouds are creating these cyclones. Is cyclone the right word to use? I mean, of course, I'm using a term that's familiar to an Earthling, but what are these storms on Jupiter? Is that an apt comparison?
So for these particular storms that we showed pictures of today, cyclone is as good a term as any. We have lots of names for the storms on Earth, and the names are related to how big they are and which direction they turn and how they formed and what causes them and so forth. Jupiter's a different planet. It doesn't have, ground and ocean and air. It has this enormously deep atmosphere that's hotter on the bottom, cooler on the top, and what drives the storms is therefore a little bit different. So it's kind of just, make up a name and move on. But in this case, these particular storms look fairly similar to what a cyclone would be on the Earth, and calling them a cyclone is pretty fair. Of course, they're really big. The cyclones in the pictures we were showing today are 7,000 or 8,000 kilometers across. So, and some of the storms on Jupiter are bigger than the entire Earth. I mean, the Great Red Spot is enormous, and calling it a cyclone or a hurricane just doesn't seem to do it justice.
If we were caught in one of those cyclones, if we could travel to Jupiter and sit in one of those cyclones, what would it be like? Would it be swirling gases? Would it be precipitation? Would it be hot? What would the experience be like?
So it would depend a lot on where in the cyclone you were or where in the storm you were. Let's just talk about storms in general. At the very top of Jupiter, it's cold compared to here on the Earth. As you go into Jupiter, you don't have to go very far before it gets to be hot. And if you go significantly down, say, 10% of the way into the planet, you're getting to very hot. So if you were just floating in one of these storms with winds moving at, say, 100 miles or 200 miles an hour, you'd be floating along in the wind, and if you were floating up high, you'd be freezing, and if you were floating down low, you'd be burning up, and maybe there's a spot somewhere in the middle if you could stay there where the temperature at least would be okay, but you'd be in these winds that are hundreds of miles an hour lasting for a very long time. So if you think about it, if the storm is a few thousand miles across and the winds are going hundreds of miles an hour, just to go around the storm once takes you quite a while.
I assume that these storms then and the conditions of Jupiter's atmosphere preclude any human space mission to Jupiter.
Well, I'll never say never, but I don't think Jupiter would be my first choice of a place to go visit in person. While I love the planet, it's really fascinating and exciting. If I did go to Jupiter, I'd want to orbit or land on one of the moons, not on the planet itself. And I also want to point out, it took our spacecraft 5 years to get to Jupiter. So if you were going to go on a trip to Jupiter, not only would it take you a long time, but our spacecraft isn't coming back. If you went to Jupiter, I assume most people who took that trip would want to get to come home again. And in order to come home again, you'd have to carry along with you a really big rocket. It took us a really big rocket to get out to Jupiter. It would take just as big a rocket to get back to Earth again. We don't know how to do that yet. We're not close to knowing yet how to send a spacecraft all the way to Jupiter and bring it all the way back. There's a really exciting idea for missions to go to, say, Mars and bring samples back. And eventually, I hope people will get to go to Mars and come back. But Mars is a lot closer than Jupiter.
Well, then finally, there are still a couple more years left in the Juno mission, and perhaps it will be renewed, but we won't go there yet. What are some of the big questions that you hope to answer and that the public should be listening for as they're following the news of the Juno mission? Just a couple central things that you're hoping to answer.
So it's hard to narrow it down to just a few, but I would say one question that we have had from the beginning that we're working on is how much water there is in Jupiter. That's important, understanding the global water content, how much water there is in the whole planet, in order to help understand how did Jupiter form. One of the key things we're trying to figure out is how did this giant planet form, and as a result of that, how did the rest of the solar system form? Because, Jupiter is more than twice the mass of all the others combined, and it formed first. So we kind of formed out of the leftovers from Jupiter. Understanding the water tells us a lot about it because, without going into all the details, in the early history of the solar system, the most abundant solid you could find would have been water ice, and the planet probably started with chunks of water ice. When we planned this mission, we thought, remember, that if you look deep enough, Jupiter's atmosphere would be well mixed. We could measure the water in one or two places. We'd get the same answer everywhere, and we'd say, okay, this is the global water content. Well, we now know Jupiter's deep atmosphere is much more complex than that. So we're working on the water content in sort of one place at a time, and also in how do we globally take all the data together and get the global water content. I still expect to get that, but it's much more complicated than we originally thought.
And that's the bottom line. Jupiter is more complicated than we originally thought. Dr. Steve Levin, thank you so much for speaking with us today.
My pleasure.
Steve Levin is the project scientist for the Juno mission. And, Molly, I was uncertain what that background noise was when you were talking to him until I realized that's what a room full of people sounds like.
Yeah, isn't that a great sound? I know we're going to hear that again soon.
I would never have called it a great sound, but it's a sound I miss, I'll say that. Well, Dr. Levin described some of the goals of the Juno mission, and the spacecraft has been orbiting Jupiter now for almost 5 years. And there's really an update because, of course, there are new results from Juno presented at the AGU.
All right, I'll bite. What are the updates?
Well, I think there's more on the lightning. They've seen thousands of flashes of lightning. And in a way, you could say, okay, maybe that's not so surprising. Everybody knew that Jupiter had some lightning, but they're seeing lightning every time the Juno spacecraft goes around the dark side, the backside, if you will. Anyhow, and they see these lightning bolts.
And what's significant about the fact that Jupiter's atmosphere can produce lightning?
Well, I think that the most interesting aspect of it is simply that normally to have lightning in a cloud layer, you need water droplets because they rub against one another. You get some friction there, and it produces the static electricity that, results in a lightning burst. But nobody expected that there would be water droplets high up in Jupiter's atmosphere. The part of the atmosphere you can see from Juno because you're looking at the outside, right? So this says something's going on there that we don't understand, that, there are still puzzles about how Jupiter's atmosphere behaves.
Well, later we continue our exploration of the solar system with a question. We've already visited one asteroid. Why go to the others?
Multiple launches of multiple spacecrafts going to small bodies, asteroids across the system. Why do we do this? Well, we do this for a whole variety of different reasons. Just because they're all asteroid doesn't mean we're asking the same question.
But first, some reports that bear on the changing climate. The world below a peat bog, the latest on the health of the Arctic, and the historic Australian fires triggering surprising atmospheric phenomena.
It's fire clouds and ice-teroids on Big Picture Science.
Well, 2020 started with us going to the big AAAS meeting, Molly, and now ends with our virtual attendance at the AGU.
That's right. And in between, we covered a global pandemic, our evolving understanding of the virus, its disparate impact on marginalized communities, the development of a vaccine, along with nutty conspiracy theories along the way.
Not to mention the ongoing global climate crisis, the possibility of life on Venus, and our continued exploration of life on this planet, including mollusks, mushrooms, and murder hornets.
There really have been a lot of stories. It's been a lot of fun, but we could not do it without the support of our listeners. So a big shout out to those who have joined us on Patreon at patreon.com/bigpicturescience.
That's right. In addition to keeping up with all things science this year, we managed to create a way for you to keep up with all things big picture science on Patreon.
By joining us on Patreon, you get early and ad-free versions of each episode, plus additional rewards depending on how much you donate monthly.
This includes the opportunity to chime in via polls, ask questions, get thanked in the podcast, and access exclusive bonus material.
Which includes extended interviews, the answers to your questions, and our thoughts on recent happenings such as the appearance of mysterious monoliths and the dubious existence of a galactic federation, members of whom allegedly live among us.
All that and more. And really, it's the perfect season to just go to patreon.com/bigpicturescience and sign up. It's quick, it's easy, and best of all, it keeps this show in production. Thanks.
Thank you.
We're offering you some highlights from this year's fall meeting of the AGU. That is, the American Geophysical Union, which traditionally means tens of thousands of scientists and journalists milling around in a conference hall. Well, there are no elbow-to-elbow crowds this year, but reports on research discoveries continue online. The effects of climate change receive considerable attention every year at the AGU, and this year is no different.
Recent episodes of Big Picture Science have detailed our fascination with fungi. Well, it's popped up again, the way fungi do. A new study reveals the effects of warming temperatures upon the intimate relationship between fungi, their mycelial networks, and carbon storage in peat bogs.
Okay, peat bogs. Those are those wet, organically rich areas you find in high latitudes filled with peat, which in this case is decaying moss. It's really not that much different from the formation of coal from decayed forests of long ago. And indeed, peat is also mainly carbon, just like coal. It's sometimes called soft coal.
Fungal ecologist Christopher W. Fernandez at Michigan State University and his team are studying peat bogs. Now, they may make up only 3% of global land area, but they are large warehouses for carbon.
They hold a disproportionate amount of carbon in their soil. So they're really, really important in terms of their carbon being emitted back to the atmosphere.
What is amazing about these networks that you're studying, these fungi networks and their mycelial networks, is how intricately woven they are with the plant root system. They really depend on each other. Can you just give us an overview of what's happening below ground in these bogs?
Yeah, sure. So, much of the nitrogen and phosphorus that plants depend on is largely unavailable for plant uptake, direct plant uptake. So mycorrhizal fungi are really important for plants accessing nutrients that they need to photosynthesize. So the fungi depend on carbon that plants allocate to them for these services.
You refer to mycorrhizal fungi. What are those? Is that a particular species?
It's a group of fungi, actually. So there are two types of main mycorrhizal fungi. You have arbuscular mycorrhizal fungi. These are fungi that are really common in tropical systems. And then you have ectomycorrhizal fungi. And these fungi are more common in higher latitude systems, like these peatlands.
Now, we've done a few episodes and interviews about fungi, and I trained myself to call them fungi. Are you going to be disappointed if I say fungi instead of fungi?
No, so if you're talking to a Brit, fungi is what they prefer. Americans tend to prefer fungi. It's only incorrect if you say fungi.
Okay, I think I'll stick with fungi. One of your team members has been using some sort of high-tech resolution instrument to be able to image this unseen world of a peat bog. Can you just give us an overview of what they're seeing, what instrument you're using and what they're seeing down there?
Sure, yeah. So working below ground is incredibly challenging because all this stuff is happening in a opaque, cryptic kind of environment. So colleagues of mine, Camille Dufresne and Colleen Iverson, have established these automated mini risotron, which are basically just cameras that go down clear tubes to image the dynamics, the production and turnover of mycorrhizal mycelium as well as roots, and the response to various climate change treatment.
So you can go underground and you can actually peer into these networks and see what's the response of these networks has been to climate change. You know, Chris, there's been a lot of study about the effects of climate change above ground, but the research that you and your team presented at the AGU focuses on what we don't see, as you've said. And what are your conclusions about how the warmer temperatures are affecting these delicate and intricate underground networks?
Yeah, so what we're seeing is that the plants in these systems are generally being negatively affected by climate change. And this effect cascades below ground to the mycorrhizal fungi that are associated with these plants, right? Because the mycorrhizal fungi are dependent on the carbon that is allocated to them by these trees. So the increase in temperature is drying out these peat bogs, right? And the plants, the trees that are in these peat bogs rely on that water for photosynthesis. Because of this, we're seeing a negative effect of climate change on photosynthesis of these trees. This negative response to climate change cascades below ground and is negatively affecting the mycorrhizal associates.
So the concern here is that these peat bogs are drying out.
That is correct, yeah. And when those peat bogs dry out, you get the speeding up of decomposition, and all that carbon that's stored in that system begins to be released into the atmosphere.
Okay, so one of the concerns is the health of the mycelial networks and the living material below ground, and I want to come back to that. But it also sounds like it may be the release of this sequestered carbon, and in that way, perhaps it's similar to the concerns about the release of methane in the thawing permafrost.
Yeah, they're similar kind of concerns. And just to go back, the importance of mycorrhizal fungi are not only important to the health and growth of trees and plants, but they're also really important in carbon storage because a large amount of carbon is allocated below ground to these fungi. Their biomass represents an important input into these bog systems.
So let's take a specific example about how this disruption to these key networks can affect the ground above, although we're not just concerned with the ground above. But if a tree seedling is dependent on these fungi networks for nutrients, perhaps the way that a baby is dependent on its mother, what does it mean for its health above ground if these networks below ground are degrading?
Yeah, so depending on the tree species, they could be very, very dependent on access to a common mycorrhizal network or, shared mycelium. So it could influence the recruitment of individuals into a population of trees. It's also really important in retaining nutrients in kind of the extended root system of the trees. So it's really important, depending on the species you're looking at, to the health and functioning of them.
Well, finally, Chris, so what was the takeaway message that you brought to the AGU meeting this year?
For me, it really raises concern, about how susceptible these organisms and their functioning is to these predicted climate change scenarios. So their function is integral in the biogeochemical cycling. And when you start to break down the networks that mycorrhizal fungi form, it's really concerning to the overall health of these systems.
Well, Chris Fernandez, thank you so much for joining us today.
Yeah, thanks for having me. It was a pleasure.
Christopher W. Fernandez is a fungal ecologist at Michigan State University.
Many papers at the AGU meeting address the health of the Arctic, whose fragile ecosystem is particularly susceptible to the warming climate. Our assistant producer, geologist Sarah Derouin, is here with an overview of the latest research. Hi, Sarah.
Hi, Molly.
What have you learned from the AGU about what's happening to the Arctic?
Well, there's been a lot of sessions at the AGU about the Arctic, but in particular, there was a press conference talking about the 15th version of the Arctic Report Card. And that is a document that is produced by NOAA, and it includes more than 100 Arctic experts from all over the world who talk about the health and the changes in the Arctic over the past year.
I see. And NOAA is, of course, the National Oceanic and Atmospheric Administration.
Yes, that's right.
What did they conclude in this Arctic report card?
They had an overarching message, which was basically that the Arctic is continuing to warm, become less frozen, and change biologically. And those changes are really happening rapidly.
What has the change been in the temperature? And I assume that there's been sea ice loss as well?
Yeah, both of those things. So the temperatures are rising. 2020 was the second warmest year since 1900. Air temperatures themselves were nearly 2 degrees Celsius warmer than average. But it's the water too. The sea surface temperatures were 1.3 degrees Celsius warmer, and summer sea ice was the second lowest on record.
So when you say 1.3 degrees Celsius warmer, that doesn't seem like much of a change, but we know that just a small degree in warming can have enormous consequences in the ocean because it takes so much energy to warm the oceans by even just 1 degree.
Yeah, it really does, and it affects so many different things. It affects sea ice cover, it affects the vegetation on land and weather. It really affects everything in the Arctic. So
the vital signs for the Arctic are not good. Did the scientists note any surprises about perhaps the speed at which things are changing?
I was struck by a particular comment from Rick Toman. He's a climate specialist at the University of Alaska and the editor on the report card. And, I'll read his quote here. And the quote was in the press conference itself, and it was also in a New York Times article. He says that nearly everything in the Arctic, from ice and snow to human activity, is changing so quickly that there is no reason to think in 30 years much of anything will be as it is today.
Do you get the sense that the scientists have become inured to their research? They're used to reporting on these dramatic changes in the Arctic?
I got the feeling that they are still amazed and shocked because every year there's a new set of data, there's a new set of observations that they just aren't really expecting. They started using words in the press conference like scarcely imaginable and extraordinary. And I think that they're still surprised by the findings that they come across each and every year.
Well, Sarah, is there any good news that came out of the Arctic report card?
Well, there was a glimmer of good news, but I have to warn you, it's not completely good news. And those are the bowhead whales. Now, bowhead whales are really unique and wonderful animals. They are the only true Arctic baleen whales, meaning that they live year-round in high latitudes. They never leave the Arctic. And they're really amazing. They have the thickest blubber of any cetacean. They can live over 200 years, and they can break the ice with their bodies. And the ice can actually be up to 2 meters thick. And they have this beautiful kind of bump on the back of their head. They're really gorgeous creatures.
And how are they doing?
So commercial whaling actually brought them to near extinction. But since the whaling stopped in the early 1900s, 2 of the populations of bowheads, and there's 4 main groups in the Arctic, have recovered nicely. And scientists really say that it's because of the conservation efforts. And it's all because of the partnerships with the indigenous hunting communities in this Arctic region.
Well, that is good news, although we were listening to you carefully, Sarah, and you did say it's not all good news about the whales. What's the bad news?
Well, I hate to be the bearer of bad news also with this story, but part of the success of the baleen whale recovery has been, at least in the short term, the actual warming of the planet. So the warming has led to less sea ice, and the warmer temperatures of the water means more zooplankton that they eat. And so there's a lot of food supplies, there was a lot of successful feeding patterns. And while this seems good, it also means that less sea ice means that their only natural predator, the Arctic orca, can now come in and hunt them. So less sea ice equals more food, but also more predation.
So it really pulls on our emotions in both ways, doesn't it?
It really does.
Well, Sarah, thank you for that report from the Arctic, a small glimmer of hope, but otherwise overall a pretty sobering assessment of what's happening. Sarah, thank you.
Thank you, Molly.
Our assistant producer and geologist, Sarah Derouin, talking with Molly. The fact that the report card is not so good again this year, as Sarah said, is just continuing a trend. Sea ice has been decreasing in the Arctic by about 5% per decade for quite a while now, and the trend is not abating. A link to the Arctic report card, including a video summary, is on our website, bigpicturescience.org. Well, the far north is not the only ecosystem changing under the influence of climate change. So is down under. The Australian bushfires of 2019 and 2020 were like nothing we've ever seen. Nearly 50 million acres were burned in mega blazes, ringing the continent and even in the dry red center. It was the country's most disastrous wildfire season ever. The heat and ash of some of these fires produced massive soot-filled clouds known as pyrocumulonimbus. The etymology there, pyro for fire, cumulo for, a mass, accumulate, and nimbus for cloud. Such clouds are also called pyro-CBs.
I've seen footage of these clouds, Seth. They're enormous. They tower into the upper atmosphere, and they're dense and pillowy like a cauliflower.
That's right, although meteorologist Mike Fromm makes a more sinister comparison.
Everybody's seen the pictures of the mushroom cloud from the atom bomb over Hiroshima. That mushroom cloud was essentially a CB, a cauliflower cloud that rose very quickly up to the top of the troposphere by virtue of just one tiny, area-wise, bomb blast. A pyro-CB is like that. You get enough of a very rapid, large area bubble of hot air from the fire that it actually will generate that thermal heat bubble, and you end up with a thundercloud. And it includes all the things we see from the thundercloud: lightning, hail, everything but precipitation, because the smoke has seeded the cloud and kind of damped down any chance for it to produce rain. So that all the smoke that goes up in that hot bubble stays up and none of it gets washed out.
Dr. Fromm from the Naval Research Laboratory describes how these towers of particulate matter, often associated with volcanic eruptions, formed over bushfires where temperatures reached up to 600 degrees Celsius, that's 1100 degrees Fahrenheit, and how his team tracked the massive amounts of soot that spread around the world.
The soot and smoke particles definitely are a major pollutant in the atmosphere. When they get up high in the atmosphere, where these firestorms inject them, they can travel across the globe and go long distances. They can have their own effect on the weather itself and also perhaps on climate, which is still something we're trying to understand.
When I think of, the residue of a fire, I think of burnt trees, kind of a desolate landscape, but I think of it being localized, not affecting me, 100 or 1,000 miles away.
Right. Yeah, well, that's a good point. And I'll refer to a series of papers that were written back in the 80s and 90s on the subject of nuclear winter. You're probably familiar with nuclear winter. Well, nuclear winter was a theory about what smoke would do if it was abundant enough in the upper atmosphere to actually shroud the Earth from sunlight and cool the Earth on a global or regional scale. The pyrocumulonimbus discovery is really very much the realization of that theory. Now, I'm not a nuclear winter expert, but I know from those authors, they said these smoke plumes that you've shown are really occurring are the real manifestation of what we hypothesize might happen. So in nuclear winter, it has real effects on growing seasons, global temperature, and things like that. And the pyrocumulonimbus storm is just one small example of what could happen on a larger scale if that kind of scenario were to take place.
I mean, how much soot are we talking about here? You give it the name of a cloud, but when I think of a cloud might be a half a mile in size or something like that.
Think of it like a monstrous chimney. So all the smoke is concentrated inside that chimney, which is the CB cloud, and then it squirts out the top, and then it spreads by the winds from a cloud-sized source to something that can cover an entire continent, let's say.
But why doesn't the soot simply fall back to the Earth in short order?
Very tiny particles.
It's like the dust in my house.
It's even smaller than the dust in your house, though. It's so small that once it gets up, it's very slow to fall down.
Okay, well, what altitude are we talking about?
Well, if you think about the top of a CB, that's up there at the very top of the troposphere where airliners fly, cruising altitude, let's say. That's the altitude where most of this stuff gets squirted out and then goes on its way. And if the pyro-CB is especially monstrous, then it will inject it even to the stratosphere above. So above aircraft altitude.
So you're talking about maybe 10 miles up or even higher?
Yep, 10, 15 miles. Yep.
Okay. And so these clouds of soot spread around the Earth. I mean, is there any limit? Do they just go everywhere?
We have found that a single pyro-CB storm can inject a plume that 3 weeks to 5 weeks later, we see from the high Arctic down to the tropics. So it'll spread north to south, almost to the equator, up to the poles, and then, like I said, completely around the world.
How long does it take before the atmosphere kind of cleanses itself of all this particulate matter?
In the case of the biggest storms we've studied so far, we have been able to detect soot or smoke particles in the stratosphere for 8 months to a year.
8 months to a year. Are there any known health effects?
Not that I'm aware of. Certainly, if you have a chimney that's shooting all that stuff up into the upper atmosphere, then there would be no health effects that I know of. Concentrated smoke, obviously, at ground levels is a health hazard. But the peculiarity of these storms is that for the time that they're occurring, they're taking all that smoke and shoving it way much higher than we breathe.
Mike, clearly climate change suggests that it's going to increase the severity and the frequency of these events. Do you see them as being something major that we're going to have to worry about? When people think of climate change, they think about turning up the air conditioner, or they think about, the fact that certain flora and fauna are going to be affected, or maybe their island nation is going to be submerged. I don't know that they think about the effect of wildfires producing these contaminants in the atmosphere.
I think my answer in a nutshell is we still don't know. But we know enough now to put it on our radar screen to try to understand them and to see if, in fact, these will get worse and more numerous in a warming climate. What I can tell you is that in the last 3 years, we've had 2 or 3 pyro-CB events, one of them being in Australia, the other being in Canada, where we've seen things we have never seen before in terms of how much smoke was injected, how high it got, how long it lasted. And we in the fire weather business call these conditions that spawn these storms hot, dry, and windy. So if in a future climate we're going to be hotter and drier and windier, we can expect more numerous storms and maybe even more severe storms. So it's reasonable to pay attention to that and try to study it better.
Mike Fromm, thanks very much for speaking with us.
Yeah, you're very welcome.
Michael Fromm is a meteorologist at the Naval Research Laboratory. Coming up, from a warming Earth, we turn our attention to icy rocks and why NASA is chasing them around the solar system.
What can these orbiting storytellers reveal about the birth of the solar system? And what to do if one gets too close for comfort? Next.
It's fire clouds and ice-teroids on Big Picture Science.
presenting stories from this fall's American Geophysical Union meeting, otherwise known as the AGU. Every year, it's the venue for the latest research in the physical sciences about the Earth and nearby space, and this year was no different, even though the meeting moved online.
One topic that got considerable buzz at the meeting was NASA's big plans for small bodies. Asteroids are the theme for 2021.
And you'll notice that we've been calling this show Fire Clouds and Ice-teroids. Well, there's no such thing as an ice-teroid. We did that in a nod to Robert Frost. But asteroids are basically balls of rock and ice, so maybe we've come up with a useful new name, Ice-teroid.
And the Ice-teroid asteroids are headed this way, at least parts of them. The Osiris-Rex mission returns to Earth in 2021 with a sample of material gathered from the asteroid Bennu. But there are more asteroid missions coming. Lucy will visit one asteroid in the main asteroid belt and 7 of what are called Trojan asteroids, while the DART mission is going to test the feasibility of deflecting an asteroid that might be headed this way.
I'm Nancy Chabot. I'm a planetary scientist at the Johns Hopkins University Applied Physics Lab, and I'm the coordination lead for the DART mission.
I'm Tom Statler. I'm a program scientist in the Planetary Science Division and Planetary Defense Coordination Office at NASA headquarters in Washington, D.C.
Well, let's start with the Osiris-Rex mission, which is coming back to Earth after being sent into space to a nearby asteroid. You know, it's bringing back a sample of this asteroid. Well, why is it doing that? What do we suspect we'll learn from that?
Well, we're going to learn how the solar system formed and what were the first solids that were. It's very exciting. I study meteorites actually a lot, so we have some samples from asteroids, but we don't know where they're from exactly, and we don't know which bodies they came from. They had a really hard journey getting here. They came through the Earth's atmosphere. We picked them up maybe right away or maybe thousands of years later. Instead, Osiris-Rex is going out there, getting this piece of this asteroid from exactly where we know it is and bringing it back here to Earth in these pristine conditions. And we're really excited about looking at this sample and seeing what it shows us about how the solar system came to be.
Okay. Well, Tom, this mission has been in the news not only because it successfully grabbed a bit of this particular asteroid. Bennu is the name. And I think all the names for this mission are taken from Egyptian mythology or something like that. But, how much stuff are we bringing back?
Well, we don't quite know yet, but the sampling attempt seemed to be so successful on video that we're probably bringing back at least a kilogram worth of material. The TAGSAM sampler on Osiris-Rex has a capacity of somewhere between half a kilogram to 2 kilograms. It's a little bit less than a pound. So we're looking forward to a big, hefty helping of rocks.
Well, why couldn't we just get samples right here on Earth? I mean, Earth was around for the birth of the solar system. Or if you don't like the Earth, we could go to the moon. That looks like it hasn't been touched much.
Well, they actually have been touched a lot compared to these asteroids. These asteroids are the leftovers of planet formation. They're the building blocks of planets. They existed before the Earth was formed and before the moon formed. The Earth and the moon have had a lot of processing. We've got a crust, we've got volcanism, we've got all of these things. These asteroids are remnants from the birth of the solar system, and that's really why they're these pristine time capsules, if you will, that let us look back in time.
Well, it seems that NASA is really down with asteroids these days because there are at least 2 other missions scheduled to go out. They seem to be particularly enthused about these small rocks.
So 2021 is going to be a really exciting year with multiple launches of multiple spacecrafts going to small bodies, asteroids across the system. Why do we do this? Well, we do this for a whole variety of different reasons. Just because they're all asteroid doesn't mean we're asking the same question.
2021 is going to be really exciting because we have the launch of Lucy and the launch of DART. 2022 is going to be just as exciting because we'll have the launch of Psyche going to the asteroid Psyche in the main asteroid belt. It's a fascinating place to go, as well as the DART kinetic impact on Dimorphos. In 2023, we're going to have the return of the Osiris-Rex sample from Bennu. In 2024, we're going to have the arrival of Psyche at Psyche. In 2025, we're going to have the first encounter by Lucy at the asteroid Donald Johanson in the main asteroid belt. So really, every year is the year of the asteroid.
Okay, well, Tom, tell me briefly about Lucy, because Lucy's going out to sample some asteroids in the coming year, in 2021. It's going to 7 different ones. The first thing it does is go to the asteroid belt. In 4th grade, most kids learn that there's a bunch of asteroids between Mars and Jupiter. But then it goes to what's called the Trojan asteroids around Jupiter. Is this a reference to, Troy or something? Why are they called the Trojan asteroids, and what's different about them?
Well, the Trojan asteroids are the last population of objects that we haven't been to yet. We haven't seen them. And they are in the orbit, in the same orbit around the sun as Jupiter. They're not orbiting around Jupiter, but they're orbiting around the sun at the same distance Jupiter is. They're called Trojans just because the people that discovered the first ones, just because they felt like it, started naming them after heroes from the Iliad, from the Trojan War. And the name stuck, and then as a group, they started being called Trojans. But they are small bodies. They're asteroids, but they're not like the asteroids in the main belt. They're not like the asteroids way out in the Kuiper belt, and we're really looking forward to seeing them for the first time.
Okay, now these Trojan asteroids, I mean, there are two groups of them. Some of them are in orbit in front of Jupiter, and some behind. This is the result of a gravitational interaction between Jupiter and the sun, right?
You're right. There are two different groups of Trojans, one in front of Jupiter, one behind. And you can think of them as either refuges or dumping grounds for leftover materials from the formation of the outer planets. And that's why it's so interesting to go there, because it's these leftover building blocks that we think have been really untouched and unchanged since formation.
All right. So
I think it's kind of weird that they're called asteroids, actually. Don't you think, Tom? I mean, because it's almost a disservice, right? Because they're kind of a different population altogether than the asteroid belt, we think.
Well, then we need some more names, because the asteroid belt asteroids aren't the same as the Kuiper belt asteroids. And, well, it's a terminology problem, but that's okay. Any small rocky thing in the solar system, it's okay to call it an asteroid. And as we learn more about the solar system, as we always do, we start learning that these different objects in different places are not the same as each other. And that's okay. It's okay to gain information.
It sounds to me like these programs are like, I don't know, walking around the kitchen and finding all the ingredients to understand how the cake you were eating was baked. But you can't just go to one asteroid, apparently. Well, one thing that we haven't talked about when it comes to asteroids is kind of an obvious subject. I mean, asteroids, yeah, they were responsible for the birth of the solar system. We wouldn't be here without them. But on the other hand, maybe we won't be here with them. They, if one hits the Earth, talk to the dinosaurs, it might be bad. Nancy, you're involved with the DART mission, and I'm sure that's an interesting acronym. What's the function of this particular mission? It isn't to get a sample.
No, it's really interesting because, asteroid missions have a lot of different purposes. And the purpose for the DART mission is fundamentally different than these other science drift missions. It's a planetary defense mission. And so what DART is, it's a NASA mission to demonstrate asteroid deflection with a kinetic impactor. So said more simply, we're going to launch a spacecraft, target a small asteroid, and slam into it. And by doing that, we're going to change that small asteroid's future path just slightly, deflect it. DART stands for the Double Asteroid Redirection Test. That T is very important. This is just a test. This is not an asteroid that's a threat to hit the Earth. Instead, it's an ideal target for this DART mission to take this first step in figuring out how would you deflect an asteroid if you needed to.
Okay, but this is only one of many ways that have been suggested to deflect an incoming asteroid. You're just going to hit it. I mean, why do you actually have to go to the expense and trouble of mounting a mission to do that? If somebody says, well, what happens when, I don't know, you shoot a metal duck in at a carnival? I kind of know what's going to happen. I don't have to go and do it. Well, why do you have to go and do it?
Yeah, so the reason that we need to go and do it is because we do know that this is going to influence the asteroid's path, but we don't actually have a good understanding for how much. From what we've seen from the science missions to asteroids, they are all very different. Some of them have big boulders, some of them are more grainy and rocky, like Tom was saying. And this can really affect how much you can deflect this asteroid. What's interesting too is this isn't like billiards. So this isn't what we expect is going to happen. We don't think we're just going to bring in the spacecraft and we're going to push the asteroid. It's actually going to have a bunch of ejecta and rocks that get shot out in the other direction. And that's going to give an extra push. We don't know how big that's going to be. And the models really need to do this real world test before you would need it for sure.
I think this asteroid you're going to hit has what you could call a moon, right? There's a second asteroid going around it. That's why the D in DART double, right? Why hit an asteroid that has a buddy? I mean, is it just because it's more fun?
So that's really what makes the asteroid system that DART is going to target such an ideal candidate, is that it's a double asteroid system. There are two asteroids, and there's the larger asteroid Didymos, and then the smaller moon asteroid Dimorphos goes around it like clockwork. Every 11 hours and 55 minutes, it goes and goes and goes. And we know this from the telescopes here on Earth. And why this is such a good way to do this first test is that we're going to slam the spacecraft into it. We have an Italian CubeSat that gets kicked off a few days ahead of time, is going to take some spectacular images of the ejecta. But how are we going to know how much we deflected this smaller asteroid? So how we're going to know that is from telescopes here on the Earth. So assets that already exist are going to be used to look at this, to see how much we changed that 11 hours and 55 minutes.
That's one of the beautiful things about DART, the double asteroid redirect test. It's a double asteroid, and it's also a double test. So double has a double meaning. We're testing both our ability to execute the kinetic impact, get to the asteroid and hit it, but we're also testing the response of the natural asteroid to the impact itself, which we don't know yet without trying.
It maybe ought to change the name of the mission to QART, since it's a double-double.
It's a little harder to say.
I suppose so.
It's the double asteroid double test.
Okay.
Like a gum commercial. I don't know.
Yeah, it sounds like something I get at the local fast food outlet. All right. Finally, let me just ask this. So I'll begin with you, Nancy. You're there at the American Geophysical Union meeting, the fall meeting of the AGU.
I mean, by there, you mean like in my house.
Yeah, well, that's right. I guess 2020, you could say, is the year in which there's no there. I think that's safe to say. But had you been there in person and gone to lunch and somebody says, well, what do you do? And you said, well, I study asteroids. What's the big message that you would tell them why they should be interested in this thing?
There are so many reasons. I think that's the thing, is that sometimes we do a disservice by lumping all of these things together because the questions are so different. We're talking about what we would do to deflect an asteroid if it was on a course on the Earth, to getting into the outer solar system to look at these objects that are perhaps from the remnants of these icy planetesimals that formed out there. So there's very different questions. And then you bring them into the lab and you can study them and you can understand our origins and the formation. So there's really a lot of varied reasons to study these things. And I think that we're always surprised. I think that's one of my favorite things about working in this field. Even when we have our theories and we think we know what we're going to find, we seem to always be a little bit surprised by what actually happens.
And you, Tom? I mean, it sounds like you're an archaeologist in a sense.
Very much in a sense. I mean, archaeologists, if they're trying to understand how an ancient temple or the pyramids were formed, they can study the pyramids, but they can learn a lot more by excavating the abandoned construction site next to the pyramids and seeing all the blocks that did not get put into the pyramid and understanding what they were made of and why. That's really what we're doing with asteroids. We are doing archaeology. And as Nancy said, there are so many different questions to answer. And the best science always opens up new questions that you would never have thought to have asked in the first place.
Tom Statler, thank you very much for speaking with us.
You're welcome, Seth, and thanks for having us.
And Nancy Chabot, it's been a real pleasure to talk with you.
My pleasure. Thank you very much.
Tom Statler is a program scientist on the Lucy mission in the Planetary Science Division and Planetary Defense Coordination Office at NASA headquarters in Washington, D.C. Nancy Chabot is a planetary scientist at the Johns Hopkins Applied Research Laboratory and DART mission coordination lead. And that's it for our show. Well, Seth, what is the big picture coming out of this big conference?
Well, one big picture item is, a big question in astronomy. How do you make planets? And, now that we're finding planets elsewhere, it's kind of important to know how you make them. Now, when I was a kid, you went to the local planetarium and they would tell you how they thought planets were formed. And all of that was wrong. So, these missions to the asteroids, they're really important. It's going to tell you how things are born.
As we learn more about other planetary bodies and about these ice bodies, we are also learning more about our own planetary body that we call home and how it's changing.
Yeah, indeed. Climate change it's like a multi-tentacled sea creature or something. You think it's just it's going to warm things up. It's going to raise the sea level and stuff like that. But when you look in detail, you see it affects all sorts of stuff. And this is a conference big enough to encompass all sorts of stuff.
Well, we could not do this show without the talents of producer Gary Niederhoff, assistant producer Sarah Derouin, and intern Frida Cryer. Thanks to them all. I am executive producer of Big Picture Science, Molly Bentley.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation and NASA. Big Picture Science is produced at the SETI Institute, a nonprofit education and research organization that investigates, among other things, the possibility that asteroids may have brought the molecular seeds for life to Earth. I'm the Institute's senior astronomer, Seth Shostak. Also, big thanks to our listeners and those who have joined Big Picture Science on Patreon.
Special thanks to a couple of our Patreon velociraptors, Damon T. Ski from Denver and Joseph Barney from North Ogden, Utah.
And members of our Patreon Dolphin Pod, William from Dusseldorf and Don Mundus.
This episode of Big Picture Science about science at the AGU meeting is called Fire Clouds and Ice-teroids. If you'd like to hear the episode again or listen to past episodes, well, you'll find them in our archive at bigpicturescience.org. And you'll also find a list there to the guests you've heard.